Welcome to this video explaining the use of the JAREmulate graphical interface. The GUI is divided into separate sections. Along the top we have the ability to play and pause networks. We have the ability to enter and exit edit mode, and we have also auxiliary tools for providing functionality, including centering the map, taking snapshots and adding impairments. On the left hand side of the user interface we have a list of devices. In this case we have an emulator on 192.168.1.100, and we then have an offline sandbox that can be used to develop emulations without any hardware. Below this we have a wizard that provides functionality including wireless internet simulation, some example emulations, and then a special conditions wizard that allows the extracting of network parameters, that is delay, jitter and drop, from a externally or recorded through the emulator PCAP file. These PCAP files are generally created using the Wireshark application. The main desktop can be moved around to provide additional space. Emulation maps are shown along the top and you can switch between them by clicking on them. And on the right hand side we have our network toolbox. This provides a list of all the available and licensed tools for the emulator. The main desktop is the area where you will build emulations. An emulator is supplied with a number of physical ports. In this example, we are creating a bridged mode emulation map. In bridged mode, ports connect directly to impairments and then to destination ports. The additional mode, virtual routing, will be demonstrated shortly. So in this bridged mode example, we're going to take a simple impairment such as delay, drag it out and then snap it into the connection between link 1 and 2. You can double click the impairment to see a range of options. For delay we have constant or linear delay with the resolution down to 0.01 of a millisecond. We have range delay between a minimum and maximum value. We have a normal distribution. We have ramp up or ramp down and sinusoidal wave. In terms then of bandwidth throttle, we drag the same tool out and snap it into the link, and double clicking it shows that we have two modes of operation: a constant throttle given in megabits per second or an auxiliary rate, and a range delay between a minimum and maximum value, changing every, in this case, 5 seconds. The JAREmulate range of products are highly flexible. They allow you to create connections between any objects, and they also allow for the duplication of impairments. In this case, for example, I have a sinusoidal delay with a constant delay, so these two operations will result in a compound operation, in this case resulting in a higher delay. This small icon along the top allows you to see the enable or disable buttons on the top of each impairment. This means at runtime you can turn off impairments to stop the effect occurring, and this allows customers to turn on and off different types of impairments to simulate higher delays or the dynamic nature of most networks. I'm going to go through each of the built-in, the core impairments one after the other before moving on to traffic generation. I'm just going to drag these out. You will notice the different colours. Orange means the impairment will corrupt or disrupt a certain part of the packets. The blue ones simply mean the packet will be delayed or disrupted. Packet corruption means that packets entering this tool will receive a level of corruption specified here. This can be either to a specific position in the packet, or to the entire contents. And we support bit flips or byte overwrites in terms of corruption. Packet drop allows you to drop a X and Y range, in this case 5 in 100, or a percentage drop, that is a percentage of received packets. The packet sinkhole has a single input and no configurable options. It is used as part of the filtering technology to drop or completely sync all packets. This can be used to effectively remove certain types of packets or to simulate an outage. MPEG in H.264 provides the ability to corrupt video streams down to unique types of framing information. In this case, IDR iframes, individual iframes, B frames and P frames can be corrupted or dropped. We can also automatically correct any checksums and notify the user of conditions where the impairment may not operate satisfactorily. Bit error rate corruption allows for a specific number of bits every Y amount of bits to be corrupted. We have quite a large variation in the values that can be supplied here. Packet duplication simply duplicates a packet at the input side to the output side. So in simple mode, one packet enters and two will leave. Under timed mode, you can have a delay between that second duplication. Or in complex mode, you can have a number of duplicates with a delay between them. Packet delay, as I previously explained, has different options, including constant, linear, range, normal, ramp and sinusoidal. One important thing to note is that we enable jitter as part of a constant delay. The reason that we do this is that jitter can be positive or negative. That means switches can delay packets slightly and then burst them slightly quicker as they were originally delayed, and this is provided through this tool. The majority of competing solutions only offer positive offset and therefore do not accurately represent jitter. Bandwidth throttle I've shown. Ethernet fragmentation. Again, this allows packets to be fragmented under a certain MTU value. We provide a dedicated jitter tool, and this is really to compete or offer a level playing field with some competing products that only offer a positive offset. So in this case, we clearly show the user that it is a positive offset that we'll be adding. And finally, packet reordering allows for a probability of reorder occurring either time-based between a minimum and maximum displacement, or through a packet distance between minimum and maximum packet distance. So that's the core set of impairments that are available. And these are the standard impairments that most people will use as part of their emulation. I'm going now to create a new map by right-clicking and selecting a basic bridged map. And this provides us with the default ports. I'm now going to demonstrate the generation of packets. In this case, we provide a background traffic generator, and this tool can be used to generate a fixed rate of data, or a percentage of the available link, or a range delay between a minimum and maximum with a change every X amount of seconds. This is simply snapped in as such. We have additional load generation tools here that are part of the virtual routing technology, which will be demonstrated later. As part of generating packets, we have the ability to generate traffic capture files. These are files that are captured effectively through the emulator or supplied from a simple Wireshark PCAP file. This can be snapped into any link. Double click to provide a name of a file along with the ability to loop this file. In addition to replaying traffic in line as such, it could also be used to be connected in other methods such as this in standalone, or we could simply delete the incoming port 1 and have port 2 receive only the replayed traffic with additional background traffic. The configuration and setup of these links is entirely up to the user, and we allow them to create both good, known good networks and also poor or bad networks. We then are moving on to the filtering technology. JAREmulate provides a number of built-in filters ranging from MAC address, VLAN and MPLS tag packets to IP address, UDP filters, video and audio streaming technologies, as well as the ability to filter X and Y packets, that's 5 and 10 or 1 and 1000. We also provide input and output switching filters that I'll demonstrate shortly, and a generic filter for custom filters. If we have a look at the IP address filter, you'll notice it has an input with a pass and a fail. Effectively, when we connect into this filter, packets entering it will be subject to a particular IP address, will then either pass or fail based on that. When we look at the options here, you'll see that we have the ability to configure the source address and the destination address. We can specify single elements or ranges. In this case, I'm going to specify a destination with no source of 192.168.1.100. This means packets for the destination of 192.168.1.100 will pass the filter, everything else will fail. So in this case, I'm going to attach the pass side, reconfigure this, the pass side to the traffic replay and take the fail side straight out port 2. So all traffic that enters port 1 that is not for this destination will proceed without any impairments being applied. Packets that are for that destination will be mixed with our traffic replay and receive additional traffic generation before leaving port 2. We allow the customer to create as many filters as they require. In this case, for example, we can use TCP filter to snap in at the existing pass connection to offer further refinement on the filter. In this case, the TCP filter can simply say, is it or is it not TCP? Or we can apply additional filtering here to, for example, identify HTTP traffic. So at this point, we can guarantee that the packets are HTTP and for that destination. We can simply fail those packets directly out, or if we want, we can provide some additional type of impairment on that aspect of the connection. As you will note, we have a second opposite direction, so effectively the top is our port 1 to port 2, the reverse direction, port 2 to port 1. You're free to completely create a duplicate of this or add completely different impairments here. At this point, it should be noted that we have these small yellow tap icons. These are our test access points. JAREmulate provides a number of different types of tap devices. We have the ability to stream directly to Wireshark, that is in real time, from this section of the network to a Wireshark application running on this machine. We also have statistical graphs, and these statistical graphs can provide background information on packet count or bandwidth. And again, these produce live graphs and reports of what is occurring at this section of the network. We also have a reporting system, and this reporting system allows us to create complex reports. I'm going to select a bandwidth report at this point, but if I move in and show the facilities of this system, we can, for example, edit this report. I'm not going to go in detail of how the analyzers work and extract information for the report, but essentially the report editor allows a customer to build up quite complicated reports for key stakeholders or management, providing a way of the emulation, sort of a flow of information up to higher management. In addition, compound operations such as sum, maximum values or averages can be generated. And the system provides a full editor environment, as you can see, as well as functions, mathematical aggregation, conversion functions right on to date, time and formatting. So this is a full editor with lots of functionality that is used generally for our enterprise-based clients. This preview shows effectively random information and the resulting summary at the end. We have the ability to traffic capture at any point in the network as well. when I had the Wireshark capture down here, this was streaming data from this point, or packets from this point, to a live Wireshark application running on this desktop. Traffic capture captures the packets passing this point to a file located on the hardware. The main reason for the difference is that when you approach higher speeds, Wireshark is incapable of addressing the number of packets it's receiving. Essentially, you get between 25 to 30 megabits per second before data is dropped, whilst traffic capture can capture traffic accurately up to 10 gigabits per second. The additional RTP and RTCP stats tabs provide information on the real-time protocol commonly used in audio and video or VoIP streaming. And finally, the load generator analyzer is provided for the virtual routed mode, and I will go into more detail on that shortly. In addition to providing these built-in filters, the packet counting filter allows for a certain number of packets to be failed in an X and Y mode, or a certain percentage. This means that in this instance here, where it's failing 1 in 1000, I could snap this into the link and effectively know that 99.99% of packets will go this way, where the 0.01% will go to failed. In this case, I can use the packet sinkhole and simply say that any packets that fail should be dropped. So this is a way of controlling packet drop using either one of these two modes. Input and output switching filters are best shown in an example network map. This map also demonstrates this facility here, which is the timeline facility. But I will go into the input and output switching filters first. Effectively, this network has a good path along the bottom with low delay and good bandwidth. Likewise, in the opposite direction, it has low delay and high bandwidth and good bandwidth. Whilst in the bad path along the top, we have a range delay and very low bandwidth, and likewise on the opposite direction. The input and output switching filter at runtime allow you to switch between each of these links with a single click. In design mode, you have the ability to provide up to 4 outputs, so you can additionally connect 3 additional outputs here. And the main use case for this is to effectively allow the switching in and out of impairments to simulate real-time changes, or switching between primary and backup or failover links. The timeline along the bottom allows you to automate the emulation map over a period of time. Whether it's a few minutes or several days, this tool allows you to place waypoints that, when set, allow you to change the configuration of the network map and have it saved against that waypoint. Each of these waypoints have been previously created, and if I press the blue button, you will notice that these links will change. So they will move to bad, back to good, to bad, to good, and so forth. When the simulation is ran, the system will tick along over time and automatically switch to the new waypoint as the time has passed. This allows customers to visually automate the impairments and change things in real time. Moving on, the generic filter is the final filter that I want to go into detail in. The generic filter allows customers to supply generic information, such as on the 8th byte of the packet, I want to look at all the bits in the packet and make sure they're set to the value 55. When I add this, effectively, I've added a filter component, which means that every packet that has this option set will pass the filter, otherwise the packet will fail. This is very handy for identifying control packet information, such as control frames in CCTV cameras, or providing ways of identifying application level packets. For example, packets that sit above the TCP and UDP layers. You're free to add up to 6 different types of filter components here. Genetic packet modification is also possible with our emulators. This means that you can modify a certain byte or range of bytes in a packet to effectively change the contents. This looks very similar to the filter component, in other words that we can give something a name. We provide an offset, how many bytes we wish to change, in this case 1. A bit mask, so in this case I can set that I'm only interested in the lower bits of the byte, and then a new value to stamp into that position and add that. So all packets that are received by this packet modifier will have the 5th bit set to 6, and we automatically fix the checksums as well. So often you find the configuration as a generic filter will identify some sort of information. This, for example, could be control information. And then if it passes, we modify that value or that control packet. For example, with a CCTV, you could have the option of sending back control information to say if the camera has panned left or right, or if it has turned on its infrared information. So a customer could effectively go in, modify that control message to say, actually, instead of the camera's panning left, I'm going to send a reset signal. And in that way they can force and test denial of service, they can test the application's robustness to somebody trying to modify the information that is flowing between their cameras and their control system. To complete the rest of these impairments, the bottom sections are the tap devices already shown. But we have a hardware-based latency tester that allows us to get to a microsecond accuracy and measure external hardware. So this means if you have a number of switches or routers that you wish to understand what the delay is through them to accurately model this, the emulator can send control messages or ping effectively messages out a port, receive it back in another port, and estimate the time it took to get through that piece of hardware. We also have a extender system, and this is really just to provide ways of better modeling the network. It provides no other functionality except for additional tap devices, but also to create better angles and better visibility on the network. VLAN instancing is the last tool we have available here. Normally in VLAN situations, a large number of filters may be required. You generally end up with a situation that may look like this. In other words, you have VLAN filters identifying single VLANs to which you're applying roughly the same impairments to it, and likewise in the opposite direction. To reduce this requirement, VLAN filtering provides the ability for multiple VLANs to be instigated with the same type of impairment. The example that is often used is that each VLAN should receive a dedicated delay and bandwidth. This means that VLANs, in this case if I set up between 80 and 120, VLANs 80 to 120 will receive dedicated 25 milliseconds, but critically be giving 16 megabits per second each. This means VLAN 81 and 96 will have completely isolated 16 megabits per second throttle. To facilitate the overriding of these values here, you simply add another VLAN filter below this impairment that has an ID within the range of the instancer. In this case, 101 will receive this type of impairments, while the rest will receive these. In terms then of the virtual router functionality, I'm going to show a brief example of how virtual routing would be accomplished. Instead of port 1 and port 5, or in this case 5 and 6, being connected directly to the impairments, port 5 and 6 are connected to a virtual router that acts as a gateway for devices in port 5 to communicate over the wide area network to devices located off port 6. The virtual router is very similar to the ADSL modem or your ISP's connection with any home or business. The router has its IP address, its subnet, and the ability to offer DHCP address ranges to devices connected on the physical port. It also has the ability to provide both, if we look here, automatic, manual-based routing, and also OSPF. So effectively, automatic is generated by the user interface Manual is created by allowing the user to set up the forwarding or routing information. Or OSPF is where the network routing protocol OSPF is used to build the routing table on the fly. If we look at the second virtual router connected to port 6, it will have a different IP address range offering DHCP to that range of machines. So machines connected to port 5, if they wished to ping a machine on the address range 192.168.1.x, the ping would enter port 5. It would be placed on the virtual router as a default gateway. It would then be routed across this connection to be then placed back up on port 6. Impairments are therefore added in between the WAN links. In this case, we're affecting everything within this link. To take this example slightly further and to give a real-world example, this is a 3-port emulation map or simulation map that is simulating a data center in New York of port 1, a Bermuda data center on port 3, and a Delaware data center on port 2. The customer has set up effective routing based on small subnet ranges, and it provides effectively routing between New York and Bermuda in this direction, New York and Delaware in this direction, and between Delaware and Bermuda in this direction. The customer in this case is using a background traffic generator to provide 30% of background traffic on this 10 megabits per second link. It should be noted that the background traffic generator has intelligence so they can understand what the line rate is without you configuring it. They have their delay of range and they have some jitter applied to it. On other links they have slightly more bandwidth available and they can turn on and off these impairments to test the functionality of their software. So this customer will run their various software releases on this virtualized network. They run the different systems at each of the sites connected to port 1, port 2 and port 3. And then they deploy with confidence to the cloud, knowing that their software will be able to withstand the known impairments and conditions on that network. To scale up the virtual routing, this example shows a multi-hop virtually routed network with multiple paths within it. Effectively, port 1 is connected to the first virtual router and port 2 is connected to the second router. These could be termed edge routers because they have physical connections to the outside world through the emulator's ports. And these internal or core virtual routers simulate multiple hops. In this configuration, we're using OSPF as configured here to effectively alert each virtual router to the existence of the other virtual routers. OSPF will send communications through these connections so that each virtual router will be able to discover the path to other virtual routers or to the physical world. This means when communications occur in port 1 for the far destination network in port 2, packets will be routed through the shortest path on the network. This small output and input, these two small output switching filters are used to basically switch in and out these impairments to simulate a break-in connection between the top half to have the system automatically recover using the bottom path. In this example, we've enhanced that original network map by adding in load generators. These TCP load generators can be configured to emit any source IP address and any destination address, configurable with a certain data rate. Therefore, this load generator will transmit on this connection those 4 different types of load generators, and the virtual router will attempt to route the packets through the rest of the network. As a target for the load generators, these LG targets provide a destination IP address. You can add multiple here. So effectively, a certain amount of traffic for this will be routed at this point down to this target. And likewise, the additional packets will flow through the link down to this virtual router, which will then be routed to this target. This analyzer will allow you to see how the quality of the packets in the connection being seen at this point. This allows customers to effectively generate load and add impairments to see what sort of quality will be maintained. In this example, the load generation is all internal. That means devices connected to port 1 or port 2 never see the load generation that is occurring within this network simulation. Therefore, devices connected to port 1 and port 2 will effectively fight for contention of these connections. Again, if we had bandwidth throttles, for example, if I were to place a bandwidth throttle in here, the traffic from port 1, if it was routed through this connection here, will be mixed in with this load generator and fight for this traffic through the traffic throttle, eliminating a certain amount of traffic at this stage. This means when those packets would finally arrive at this virtual router to be passed up here, there would be a certain number missing because they had to fight for contention of this internal network. JAREmulate provides the ability to generate internal load generation or to have the traffic routed out. In this case, it's simply a matter of adding an additional load generator that targets a device on port 2. To complete the demonstration, we have a number of options available on the hardware unit itself. We have the ability to rename it, to set the mode at which it operates when the unit resets, have our SNMP traps for alerting users to any problems or start and stop systems, and we have a force reboot. Our control port is available here, along with license and versioning information. This concludes the overview of the graphical interface.